In this vast cosmos, there is only one place we know where humans can survive. It seems as if the Earth was made for us. It supplies us with water to drink, food to eat, and air to breathe. It's the only home we have, and we rely on it entirely. But 5 billion years ago, it did not exist. Where the Earth now sits in the outer reaches of the Milky Way galaxy, there was just a large cloud of gas and dust. This is the astonishing story of what transformed that cloud of dust into the planet we know today. One person who understands what it takes to build a planet is astronomer Tom Fleming. Using telescopes like these at Kitt Peak in southern Arizona, astronomers have pieced together how the Earth was born.
It all begins with a big cloud of gas and dust, little particles of dirty stuff, grains of sand, grains of silicon.
Scientists call these regions of dust and gas molecular clouds. But they're not like any clouds we see on Earth.
Molecular clouds are vast. They cover hundreds of light years in size.
It was from clouds like these, photographed by the Hubble Space Telescope, that the Earth formed. The clouds are made up from the debris of hundreds of dead stars. When stars from the early years of the universe burned up their fuel, they exploded and showered the surrounding space with their ashes.
When the first generation of stars died, either gently or explosively in an event we call a supernova, the heavier elements, the irons, the silicons, aluminum, nickel, that was created in the star is blown out back into the galaxy.
This cocktail of elements creates a molecular cloud. From this, new stars are born, and planets. The force that drives their creation is gravity. The same force that attracts apples to Earth will attract two objects in space toward each other. It draws the dust particles of the molecular cloud together. Over the next 10 million years, the molecular cloud slowly contracts under the force of its own gravity.
As our gas cloud collapses under the force of gravity, to become a star, something very interesting happens. And I'm going to try and demonstrate what happens with these two lead balls and this carousel. Now I'll step up here on top of the carousel. I've now increased my mass by the mass of two lead balls, and I'm holding them straight out. So now the mass in my body is distributed at a distance far from the center.
Fleming is impersonating a molecular cloud. The weights represent its mass, which to start with, is spread over a huge area.
Now I'm going to ask Lucy to give me a hand here and give me a little bit of angular momentum. As I start spinning, I'm going to move the balls closer to the center of my mass, and notice how faster I'm spinning. And when I bring them out, I slow down again. And as you can see, this is exactly what happens to the interstellar cloud.
The large molecular cloud had a small rotation. When it shrank, this rotation speeded up. As the cloud contracted, the energy of the material flying in from space caused its center to heat up. This spinning ball became our sun. The rest of the cloud was spinning so fast that it spread out into a vast disk of dust and gas. This was the cradle of life, the material that would form the Earth and all the other planets. Until recently, What turned this dust into a planet was a mystery. Then, in March 2003, a lighthearted experiment on board the International Space Station led to a significant discovery. Astronaut Don Pettit was curious to see the effects of weightlessness on different substances. In a series of simple experiments, he filmed bubbles, indigestion tablets, swirls of colored water, then filled the plastic bag with salt. This last experiment turned out to be a scientific revelation. But at the time, Pettit didn't realize its significance. The person who worked out what it meant was fellow astronaut Stanley Love.
Don likes to mess with things, and one of the things he messed with was putting things in plastic bags, granular solids like sugar, salt, instant coffee. He put them in a bag, inflated the bag, and shook them up just to see what would happen. And what happened was the little particles formed up into clumps like dust bunnies instantly.
When he saw a video of the experiment, Love realized that he was witnessing a significant discovery.
And Don shot this video down. He said, "This is cool, isn't this neat?" And showed all his little videos and his different substances and the different bags. And I said, "Don, yeah, that is neat. Actually, you've solved a very old problem in planet formation."
In zero gravity, the crystals behaved completely differently to the way they behave on Earth. Love recognized what was making them stick together.
Well, anytime two different materials rub together, you can have a few electrons get traded off from one material to another. This happens when you rub a rubber balloon on your hair and stick it to the wall. As it turns out, once you get dust or basically anything in zero gravity and shake it up, let it bump into each other, we think it gets some sort of electrostatic charge on it, which makes it clump up together just immediately. You can break up the clumps by shaking the bag up, and then they reform as soon as you stop shaking it.
In the first few seconds of its life, our Earth may have looked something like this. Scientists think that this moment occurred 4.5 billion years ago. To follow the evolution of our planet, naked science is going to represent the time from then to the present as 12 hours on the face of a clock. At noon, the clock started ticking. The Earth's journey toward becoming a planet that can support life has begun. The first step didn't take long. Once clumps of these particles had grown into objects about 1/2 mile in diameter, their mass was great enough for their gravitational pull to attract material from the surrounding disk. Like giant vacuum cleaners, they circled the sun, sucking in material from the disk until there was nothing left to consume. In the inner solar system, these clumps grew into around 20 planets. This process took about 3 million years, less than 30 seconds on our clock. The next stage of the Earth's evolution was incredibly violent. As these 20 planets orbited the Sun, their gravity affected each other, and they began to collide. With each collision, 2 planets combined. Over time, these collisions reduced the inner solar system to just a few planets, including Venus, Mercury, Mars, and Earth. Astronomers believe that the Earth grew to this stage in around 30 million years. We are now just 5 minutes into our story. But what was early Earth like? What would happen if a human had landed here? The energy from the collisions with other planets made the Earth incredibly hot. At around 8,500 degrees Fahrenheit, its temperature is more than 5 times that inside a cremation furnace. A human would almost instantly disappear in a puff of steam and ash. But even as our planet cools down, another danger threatens. A storm of charged particles is approaching the young Earth. It's so intense that it could end all chance of life. Four and a half billion years ago, a giant cloud of dust collapsed to form our solar system, the Sun, planets, and Earth. But as the newly formed Earth began to cool, it faced one of the biggest threats to its existence: a hurricane of deadly particles from the Sun. Boulder, Colorado. At the Space Environment Center, meteorologists monitor the storms on the Sun. It's the most extreme weather you're likely to see. A light breeze out there is 200 miles per second, and a low temperature is 8,000 degrees Fahrenheit. Around-the-clock surveillance is necessary because storms on the Sun affect us here on Earth. Space scientist Rodney Viereck knows just how deadly the Sun can be.
The Sun is a large explosion, and from that explosion, energetic particles are released.
These particles make up the solar wind, and they travel toward Earth at speeds of up to 1 million miles an hour. If the solar wind becomes too strong, it can kill.
We watch the Sun, and when we see something that may produce energetic particle events here at Earth, we try and warn astronauts, even airlines, about these types of events.
The charged particles in the solar wind are a form of radiation that can cause lethal damage to living cells. An intense solar storm could kill an astronaut caught in space. But the solar wind can also have a devastating effect on planets. The Earth is surrounded by an atmosphere, a thin layer of gases that protects it from the extreme temperatures of outer space. But when the charged particles in the solar wind hit a planet's atmosphere, they can strip it away. You can see how destructive the wind can be by looking at Mars. Over millions of years, the solar wind has blown away most of its atmosphere. Now there is no liquid water on the surface, too little air to breathe. This could have been the fate of the Earth. So why wasn't it? The answer lies in the moment of the Earth's creation. As the early Earth was forming, the energy released as material hit the planet produced heat. The heat became so intense that even rock melted. The lightest elements in the molten Earth rose to the surface, while the heaviest elements, including iron, sank down toward the center. Here, they formed a molten core. It's this iron core that protects us from the deadly effects of the Sun's rays. Exactly how the Earth's core protects us is a mystery that drives the research of Dan Lathrop. In his laboratory at the University of Maryland, he spins scale models of the core to study how it behaves.
The Earth's core has dynamo action that makes a magnetic field. And that's a process where currents in the liquid iron cause magnetic fields.
Lathrop has found that the spinning motion of the core creates a magnetic shield that surrounds the Earth.
See, it's mostly axisymmetric, but you're getting small details that are rotating around with the inner sphere.
To show how it does this, Lathrop has rigged up a simple high school experiment.
We can see how the currents produce magnetic fields with this simple demo. Just take some iron filings and sprinkle them down around this coil of wire.
This coil of wire represents the core of the Earth. The iron filings will reveal the shape of any magnetic field.
And then hook the coil up to a power supply. You can see the iron filings line up with the magnetic field lines, and the magnetic field lines are passing through the center of the coil and looping around the ends.
The electricity in the coil produces a magnetic field. The same thing happens on a larger scale with the Earth's core. Its magnetic field gives our planet its north and south poles. It also extends far out into space. It's called the magnetosphere, and this is what protects us from the solar wind. As particles from the sun fly toward the Earth, the magnetosphere blocks their path. Those that get through are deflected toward the poles. Here, as they enter the Earth's atmosphere, they react with molecules in the air to create the aurora. The northern and southern lights. Today, the solar wind still erodes our atmosphere, but thanks to the magnetosphere, the loss is not life-threatening.
It's been estimated that between 5 and 10 pounds a second of our atmosphere are dragged out into the solar wind. Fortunately for us, even at that rate, the amount of time it would take to deplete our atmosphere would be many times the life of the sun.
The magnetic field produced by the iron in the center of the Earth played a vital role in our planet's evolution. Without it, we wouldn't have any air to breathe. On our clock, in which 12 hours represents the whole history of the Earth, just 6 minutes have passed. The Earth still doesn't look like the planet we know, but could a human now survive on its surface? It's possible that the Earth may have cooled enough for a human to survive in a heat-resistant suit. And thanks to its iron core, our planet is now protected from the solar wind. But there is still no oxygen or water on Earth. We wouldn't last a minute. Worse still, if a human could survive, they would be in for a shock. An astonishing event is about to take place. The Earth is on a collision course with another planet and about to experience the biggest bang in its history. So far, we have seen how a giant cloud of gas and dust collapsed to form our solar system, and how the Earth's molten iron core created a magnetic field that protected the planet from the deadly effects of the solar wind. The Earth's formation was a violent and dramatic process, but an even more astonishing event was about to take place. A collision so large that it would melt the whole planet. And the only reason we know this event happened is thanks to a large object circling over our heads. The moon is the Earth's constant companion. For centuries, humans wondered where it came from. There were many theories. Some thought that it was formed by the early Earth spinning so fast that it threw off material into space. Others proposed that the moon was a passing planet captured by the Earth's gravity. But no one really knew. In 1963, the United States launched the Apollo program. One of the mission's aims was to discover how the moon was formed.
Houston, Sweet 16 has arrived. Okay. Ron, you go for landing. Okay, down at 3. Stand by for contact. Contact. Wow! Oh, man! Fantastic!
In the late 1960s and early 70s, American astronauts made 6 visits to the moon. They played golf, tested their skills at off-road driving, and collected 840 pounds of moon rock for scientists back home to study.
How about rolling that one over? No way.
The pieces they brought back to Earth revealed something strange. When scientists examined them, they found that they were very dry, as if they had been heated. This was baffling. Any theory of the moon's creation needed to explain this mystery. In the 1990s, planetary scientist Robin Canup decided to put a new theory to the test. Using a supercomputer simulation, she modeled what would happen if the Earth collided with another planet. The results were a revelation.
This is a simulation of a single impact by a roughly Mars-sized planet, shown here in the upper right, colliding with the young proto-Earth, represented by this object here. So the impactors come in and hit the Earth at a very oblique angle, at about 45 degrees, and you can see this long arm of material right here. That's actually the impactor. It's been stretched out and distorted by the impact event itself. There's an inner clump of material, you can see it right here, that will re-impact with the Earth. After a little more time, this outer clump of impactor material, it makes a very close pass by the Earth. As a result of the Earth's gravity, this initial clump is sheared out into a long arm of material, which then finally breaks up to form a disk. And it's from this disk of material orbiting the Earth that we believe the moon then later accumulates.
From this simulation, Canup has figured out exactly what happened during the impact.
There would have been this unbelievably large impacting planet racing towards the Earth at a speed of 7 miles per second. This would have been an enormous object, a planet that was half the size of the Earth itself, and so would have completely filled the sky just before impact. The impact itself was an incredibly energetic event with enough energy to completely melt the whole of the Earth and vaporize a significant portion of the rock in the Earth.
When the planet hit the Earth, the glancing blow smashed material into space. Much of this debris stayed in orbit as a vast disk of rock and dust. A clump of this circling material then became large enough for its gravity to suck in other matter from the disk. And this became our moon. It's now 50 million years since the Earth began to form. On our clock, in which 12 hours represents the whole of Earth history, still only 8 minutes have passed. At this stage in its life, the Earth appeared very different to the planet we know. The ground remained molten from the impact for thousands of years, and the moon was 15 times closer than it is today.
You can imagine what is now a stunning sight on a full moon night would have been breathtaking at that time, with the moon 15 times larger than we currently see it.
The collision with the planet and the formation of the moon were key events in creating an Earth fit for life. The collision could have tilted the Earth on its axis. This tilt gives us the seasons. Thanks to this tilt, the Earth's climate changes gently through the year. It gives us the annual cycle of life. It may have been possible for life to evolve on Earth without these seasons, but it would have been a very different planet from the one we know today. The creation of the moon also gave us the tides. When the moon was close, these were much stronger, but they have weakened as the moon has slowly drifted away. Nowadays, we take the oceans for granted, but 4.5 billion years ago, they didn't exist. And without water, there could be no life. Where all our water came from and how it got here is one of the most amazing stories in science. Naked Science is investigating the birth of the Earth. How did nature build a planet on which humans could live? So far, we've seen that the Earth formed from a giant cloud of gas and dust. Its iron core created a magnetic field that protected it from the deadly particles of the solar wind. And it survived a big hit from another planet. But for the Earth to have life, it had to have water. Where that came from is one of the great mysteries of science. There are currently around 326 million trillion gallons of water on the planet. That's 394 trillion Olympic swimming pools. But many astronomers think that if the early Earth contained water at all, it had very little. At the time the Earth was forming, the inner solar system was too hot for liquid water to exist. The region from the Sun to the asteroid belt was almost bone dry. The nearest water reserves to the Earth were now 160 million miles away, in the outer asteroid belt. Out here, far from the Sun's heat, water froze and was incorporated into the forming planets and other objects. But how the water could have traveled from here to the Earth is a mystery scientists are only just beginning to solve. One clue came with the blastoff in January 2005 of an unusual NASA spacecraft. Named Deep Impact, its mission was to fly 270 million miles to a comet named Tempel 1 and launch an 800-pound copper impactor into its surface. The mission was the latest attempt to understand some of the most mysterious objects in our solar system. For centuries, people had argued that comets had brought water to Earth. When they looked at the moon, it was clear from the craters that its surface had been bombarded by large objects. Similar objects must also have hit the Earth, although our planet's much more dynamic geological activity has since erased all trace of them. scientists also felt certain that comets contained water in the form of ice. But the Deep Impact mission was the first time anyone had probed inside one. On the morning of July 4th, 2005, NASA scientists waited anxiously as the impactor approached the comet at a speed of 23,000 miles per hour. It scored a direct hit. The explosion was captured by telescopes around the world. Analysis of the debris confirmed that comets contain significant amounts of water. But could they have brought that water to Earth? Using radio telescopes, astronomers have studied the type of water in the vapor trails of comets. They wanted to know if it matched the water on Earth. So far, scientists have only analyzed 3 comets, but the results are not encouraging for the comet theory. The water in all these comets was not the same as the water in our oceans. The comet theory isn't yet dead, but it's fizzling out of steam. In its place, scientists have evolved an exciting new idea. A vital clue arrived on January 18th, 2000. That evening, the sky above Western Canada lit up with a bright light. Dozens of witnesses saw a meteorite enter the Earth's atmosphere. Seconds after the event, local photographers took these pictures of the trail it left in the sky. As it fell to Earth, the meteor broke up into dozens of pieces and landed on Tagish Lake in British Columbia. Within days, scientists were on the scene extracting the frozen remains. The pieces they pulled from the ice were the best preserved meteorites ever recovered. Still intact, a piece was shipped to NASA's laboratories at the Johnson Space Center in Houston. Here, space scientist Michael Zelensky examined it. The meteorite was remarkably undamaged, despite heating up through friction as it entered the Earth's atmosphere.
The meteorites, they're cold-soaked in space for millions of years. So they're very, very cold. And they enter the atmosphere at high velocity, and they do in fact get very hot on the outside, but they're only heated for a few seconds. And that's not long enough for the heat to get all the way in past a few millimeters, actually.
This means that when meteorites hit the ground, they cool very quickly.
You hear of reports of meteorites causing fires on the ground, things like that. That's always wrong. They're actually quite cold to the touch after a few seconds.
But when a meteorite is fragile, like the one at Tagish Lake, where it lands makes all the difference.
We're lucky it fell in a frozen lake. If it had fallen anywhere else, it would have easily fallen apart to dust in a few days. And so it's quite possible this kind of meteorite falls to Earth very, very commonly. It's just usually destroyed.
Because the inside of the meteorite remained frozen, Zelensky was able to analyze what it was made of.
This is a sample of the Tagish Lake meteorite. The black material here is mostly clay minerals, the kind that you'd find in your yard. And these clay minerals contain water molecules trapped inside. And so about 20% of this meteorite by weight is water. That's a huge amount.
From the location and angle at which the meteorite fell, astronomers traced its orbit back into space. They discovered that it came from the outer reaches of the asteroid belt.
If you do telescopic observations of asteroids, what you find is, as you move farther and farther from the sun, the asteroids have more and more water.
Now, astronomers suspect that asteroids from this outer part of the belt brought water to Earth. If they're right, our oceans came from space in a torrential shower of meteorites. But one question remains. What could have caused so many asteroids to swing out of their orbit and come crashing to Earth? The culprit appears to be the biggest planet in the solar system. Jupiter lies just beyond the asteroid belt, and its mass is so great that its gravity disrupts the path of any object it comes near. In the distant past, it pulled thousands of asteroids out of their normal circular orbits into elliptical orbits that crossed the path of the Earth. When that happened, collisions were inevitable. The Earth was bombarded. As the asteroids crashed to Earth, they smashed apart. Water inside them escaped. Explosion by explosion, they created the oceans we see today. Scientists used to think it took hundreds of millions of years for the Earth to acquire its water, but recent evidence suggests it arrived remarkably quickly. The evidence comes from research carried out by geologist Stephen Moisish. In his laboratory in Boulder, Colorado, Moisish took some of the oldest rocks in the world and ground them down. From inside them, he extracted tiny crystals called zircons.
Zircon is a common mineral. It's generally small, it's hard to destroy.
Using an ion microprobe, Moisish then analyzed the zircons and measured the composition of the oxygen inside them. He found that the crystals had formed from a particular type of rock, one that could only have existed if there was water on Earth.
What was startling, exciting, fun was that these zircons showed not only that things on the Earth's surface had stabilized to within normal conditions, but that water was present, and water was present everywhere.
Moisish estimated the time the Earth acquired its water from the age of the zircons.
The zircons in some of the rocks there are very close to 4.4 billion years old.
This evidence suggests that the Earth's water arrived in less than 150 million years. On our clock, on which 12 hours represents the whole history of the Earth, that's just 25 minutes after the planet began to form. At this time, our Earth would certainly have looked very different. The sea was full of iron, much of it brought up from below by hydrothermal vents, and the atmosphere was a lot thicker than it is today.
An ocean rich in iron would have appeared green. A denser atmosphere would have given a reddish tinge to the sky.
Conditions for human existence are looking better. The land has now cooled to a tolerable temperature, and there is water to sustain life. But there is still one horrendous problem. The gases in the atmosphere are mainly nitrogen, carbon dioxide, and methane. There's not a lungful of oxygen in sight. Without oxygen to breathe, there's no way a human could survive. In the early years of its life, the Earth experienced a violent and tempestuous onslaught. In time, the activity slowed until 500 million years after it began to form. The Earth had cooled and was covered in oceans. But there was still no oxygen in the atmosphere. Without that, animals and humans could not exist. One scientist who has investigated how the Earth acquired its oxygen is geologist Martin van Kranendonk. His research has brought him to Shark Bay on the west coast of Australia. It's a World Heritage Site, home to vast meadows of seagrass, dugongs, and tame dolphins. But Van Kranendonk has come to visit much older living things. This is one of only 2 places in the world where these strange living structures, called stromatolites, are known to exist.
These stromatolites have been growing here since the end of the last ice age, about 10,000 years ago. And at that time, the sea level was a little bit higher. And so these structures grew up to the present height that you see them.
Stromatolites are primitive structures. Here they come in 2 forms: short pillars of living bacteria and silt, and flat bacterial mats. The living part of the stromatolite is made up of blue-green bacteria that grow using photosynthesis. They take energy from the sun and convert carbon dioxide into oxygen.
It's really the result of this process of giving off oxygen that we have planet Earth as we know it today, and habitats that people like us, humans, and all the other animals and plants are able to live on planet Earth.
What makes Van Kranendonk believe that stromatolites created the Earth's oxygen is a remarkable discovery 1,000 miles away in a remote region of North Australia. This is the Pilbara, one of the oldest landscapes in the world. If you want to find out what happened early in the Earth's history, this is the place to come.
It's really like you're transported back into a time machine of early Earth. It just sort of gave me goosebumps and shivers to walk over this ancient environment where you could still see the processes that happened 3.5 billion years ago.
Here, at a location kept secret to preserve them, lie the oldest fossils ever discovered. The ancestors of the stromatolites in Shark Bay.
What's remarkable about this outcrop in the Pilbara is that it contains the oldest evidence for life on Earth. We're looking at here in front of me our great-great-great-great-great-great-great-grandfathers and grandmothers.
No one knows how life on Earth began, but these amazing fossils suggest that it emerged very soon after the planet formed. These fossil stromatolites are 15 times older than the dinosaurs. The bacteria that made them were living here just 1 billion years after the birth of the Earth. On our 12-hour clock, the time is now 20 minutes to 3.
These would have been the first organisms that would have started the process of change of Earth's atmosphere to an oxygen-rich atmosphere, which has allowed us, mankind, and all the rest of life that we know today to evolve on planet Earth.
If stromatolites existed on the Earth 3.5 billion years ago, they should have started to increase the amount of oxygen in the air. But it appears that they didn't. For the next billion years, the oxygen level in the atmosphere hardly changed. What happened to all the oxygen the stromatolites produced can be seen 300 miles away in this gorge in Australia's Karijini National Park. Hidden in these rocks lies the key to the mystery of the missing oxygen. Geologists call these rocks banded iron formations, and they believe that they owe their existence to stromatolites.
Well, these banded iron formations are the product of a remarkable set of circumstances in Earth history. They formed about 2.5 billion years ago when the Earth was very young, and are the product, we think now, of microbial action in the ancient oceans.
The Earth's early oceans were full of iron. As the bacteria in stromatolites bubbled out oxygen, it reacted with the iron in the water. You can see what happened in this simple experiment. This flask of water contains iron. It's the same color as the early oceans on Earth. This pump does the work of a stromatolite pumping out oxygen. As the oxygen bubbles through the water, it reacts with the iron to form iron oxide, and it precipitates out as rust. There was so much iron in the oceans that for over 1 billion years, it absorbed nearly all the oxygen that the stromatolites produced. As the rust precipitated out, it fell to the bottom of the ocean and was turned into rock. It has been estimated that around the world, these rocks have locked inside them more than 20 times the amount of oxygen that is in the atmosphere today. And they took an incredibly long time to form. On our clock, in which the whole history of the Earth is represented as 12 hours, we can see that the planet forms in the first 8 minutes. After 25 minutes, it has cooled and collected water on its surface, but it takes another 4.5 hours to remove most of the iron from the oceans and deposit it in these rocks. Only then does the oxygen level in the atmosphere start to increase. This happened approximately 2.5 billion years ago. And for the next 2 billion years, the level rose. Until just 500 million years ago, it reached the level at which animals could survive. So is our planet finally fit for human life? By this time, it has certainly cooled. There is water to drink and air to breathe. If we could travel back to this time, we could certainly survive. In our story, 11 hours have now passed. But the Earth still has a long way to go before the first humans will walk on its surface. At 37 minutes to midnight, dinosaurs will emerge. At 10 minutes to midnight, they will be wiped out by a catastrophe. Finally, at 19 seconds to midnight, the first humans will appear. It has taken over 4 billion years. But out of a vast region of freezing dust and gas, the forces of nature have created the only safe haven we have in the universe. Our home, the Earth.